Okay, we are going to start still section 2.1, and we'll continue doing this today, and we're going to move on to section 2.2. So section 2.1, type of the explosive is 2.1. This is we cover up to here. And this section 2.1-6, the type of the explosive. There are two types of the explosive. One is pure explosive. Another one is explosive mixture, or it is called the high explosive. The pure explosive is very, very sensitive. You can't touch it. Explosive mixture, I usually call the high explosive, is less sensitive. You can touch it and it doesn't explode. But if you drop it, then you got the problem. So the pure explosive is just a compound, but it's a one type of the compound, usually just a white color compound. And one substances, single chemical substances throughout the body, but the characteristics of these two explosive are totally different. Densities are different, detonation speed is different, and personality is, simply speaking, quite different. But in a bomb, it has these two different types of explosive, not just the high explosive, but I will show you, of course, a basic concept in a bomb using the explosive. And this explosive mixture is a mixed grain. It's not just one kind of chemical compound. It's a mixture of various compounds that depend on what the bomb would do at the time of explosion. So that's why you heard some years ago, one of the university students just went into the library. He was able to design the bomb, nuclear bomb. No classified information. He accessed all available literature in the book. He was able to design not only bomb, nuclear bomb. Then it was a big surprise, and there were lots of news saying, what we're gonna do? Well, all the information in the library, he accessed it, so made a bomb, same thing. To make a bomb is simple, but nowadays it's so sophisticated and would be quite different. So this is a very popular type of the explosive. This is still very fundamental information. But if you look at, there is a book called Explosive. It's not classified, it's unclassified, from the Livermore National Lab. I have a copy. It's anybody can purchase. I bought a few, and it's up there. And two different types. It said explosive and basic formula, density. This is a gram mass per cc, and the detonation velocity, feet per second. All this is what the unit-wise is U.S. gravitational unit is what U.S. is using it, but you can convert easily. And the detonation heat. But this detonation the heat for underwater explosion is not really greatly important. Two different primary explosive. This is most popular. Lead, azide, mercury, the fume. And as you look at it, this density is 3 to 2.5, and the detonation velocity is about 13,200 feet per second. Detonation heat is 370, about 400 calories per the gram mass. But if you look at the high explosive or explosive mixture, typical one is a TNT. And there are RDX, COM-B, HBX1. TNT is using for the lab environment quite well. It's all the time. I was using TNT, and the COM-B, HBX1 is a Navy explosive, and for the ship shock trier, U.S. Navy is using HBX1, which is about 50% more higher strength than the TNT. So when you're dealing with the strength of explosive, TNT is a kind of the basic measure. Comparing with the TNT, what would be the strength of HBX1? So said HBX1 is about 50% higher strength than TNT, okay? And of course, aluminum compound sometimes make it different to really change the explosive characteristics, okay? Then you have to going into material structure. Pentolite is used somewhat for the lab-based test. Tetryl is another kind. It's all various type of explosive. So I can say here, TNT is commonly used. HBX1, and U.S. Navy is using all the time. Pentolite, tetryl, PTN is using quite well. But as you see here, the density, if you compare with the primary explosive, or you call pure explosive, is the same. And this is a 3 gram mass per cc. But if you look at this, is about the half of pure explosive. So that density is, this is really compact, okay? And as you look at the detonation velocity, high explosive detonation velocity is twice faster than a pure explosive. And detonation heat is concerned, high explosive is very high compared to the pure explosive. All this chemical composition, I think you can read it better than I read, so you can see that. Just to get the feel free. If anybody can pronounce this, go ahead. All this is lengthy one word, but that's what the original name is. But simply the brand name RDX is sufficient, rather than try to pronounce this. Okay? Okay, this is a basic bomb structure. This is really fundamental. And this is a cylinder, it's a shell. It could be a steel, aluminum, whatever, okay? to make a confinement. It's just to make a confinement of explosive jar, you can say. And here, this is a small booster. There is, of course, another small booster inside. And this is a shell, another confinement. Could be aluminum, thin aluminums, whatever, okay? And over here, this is a detonator. Right here is another small confinement or little small cylinder type where the pure explosive, they put that in there. And pure explosive speed is half the speed of high explosive. So when it detonates here at the pin, okay, you call the detonator or pin, then it spread rather slow speed. Of course, it's over 10,000 feet per second. And then powder is spread out, for in the high explosive in the booster. Then it keeps spreading. Then right here it will bust. Then spread all over here. And here you have tons of large volume of high explosive contained here. Then at the moment, shock wave will really propagate. It just, all this shell will be fragmented, then spread out. So usual size is, length is about twice of the diameter of the bomb. But nowadays, it's totally different. They design, this is basic, because nowadays all the design to partition the compartment, because at the time of explosion, the fragmentation could spread all over. Then again, after it spread all over, that little pieces will explode again. So it's like the bomb shower. There are a lot of different concepts. So one sad thing is, usually U.S. and European countries, they make such a bomb, test where they're going to test, where the war breaks off. They just use a bomb to test out how good that bomb is. That's a terrible thing. And they have a stockpile of the bomb, nuclear bomb too. So in a sense, world is kind of dangerous all the time. So it look like the world, the different sites are a location for bomb testing, which is really not desirable. But I feel we don't need a bomb. But for protection purposes, defense purposes, a lot of different countries generate a bomb, but your generations should think some more than my generations. So right now, Iranian countries, they are on the verge of generating nuclear bomb. So European countries and US, they try to stop to produce a bomb. If a bomb, nuclear bomb, when I say bomb, get into the hand of the bad people, then what happened? World is dangerous. So that's what, but anyway, this is the subject. What happened, explosion occurs in the water. Is there any way we can mitigate such a threat? That's what we try to understand, but to protect people or buildings, whatever, from bomb explosion, you have to know the strength of the bomb. What's the inside story of the bomb? How we're gonna protect our life from the bomb. That's what our interest is. That's what you have to learn what's in there. Nuclear, we are not gonna bother to do. And when I write this note some years ago, I wrote something, then afterward I feel, geez, I should talk some more. Then that's why it has more on the shock wave. This is a location of explosions, okay? And this is the physical distance. So this means 5 feet away from the charge, 45 feet away, 50 feet away, all the way to 500 feet away. And this happened to be 300-pound TNT, okay, in underwater explosions. So ground explosion, air explosions, basic characteristics are very similar, okay? But the difference between air explosion and underwater explosion, what's the big difference in their characteristics? What's the big difference? Anybody can tell? Yeah, the water is really act as a pocket which confine the propagation, which confines the explosion of explosive, you know. But in the air, density is so low, and nothing would stop. But one characteristic difference in one characteristics in the air, as we learned before, is it getting hot? Or am I hot? Are you feel a little bit hot, or are you okay? I think last night the airport was so hot, so cold, so I didn't wear enough. So this morning I feel let's wear something really warming up. That's why I took this. Okay. Air explosion. When you hear the air explosion, there is a negative shock pressure is there. Did I tell you about that, right? Just to draw back. Not only the shock pressure is propagate in the positive the direction, but it also sucking back. So pressure wave goes up, right, straight up, then coming back down, still over pressure. Then now it goes into the under pressure, which means the tree is here, and shock wave in the air gonna be hit. Then when it go down to the negative pressure, it draw back. Not only hit this way, but take it back. So this is really bad for the building. When shock wave hit to the building, so one of the safety measure is always saying open the window. Why open the window? It draw back. So it will just explode more, not just going into it, but draw back is really bad. But in underwater explosion, one noticeable thing is has a gas bubble oscillations. Gas bubble oscillation, that's what the bad thing is. for the confined explosion, small charge will really deliver tremendous power. And airplane, you remember some 20-some years ago, one young North Korean woman, they concealed the bomb in the plane, then she came back out, but it exploded. But you can't even find any pieces because it's confined explosion. Small charge will deliver the power because of the confinement. That's what that is. Anyway, this is, look at this. This is only 300-pound charge, which is a 150 kilogram charge. This is TNT. 5 feet away, it generates 34,000 psi, and as it go down to 500 feet away, remaining pressure is 160 psi. So as you look at, this is high, then exponential decay along the distance. Okay, so that's what you have to consider. In the tail end is, of course, sort of the exponentially decreasing, or 1 over the distance proportional to 1 over distance, vice versa. And it's getting spread more. So it's only 500 feet, 34,000 psi down to the 160 psi. So just to get the feel of it, okay, feel. Shock, this is a shock wave, not the bubble. So propagating the velocity near charges 3 to 5 times of 5,000 feet per second. 5,000 feet per second is acoustic velocity in the water. Usually converge into the acoustic velocity in the media. So pressure profile is proportional to 1 over d, and in chapter 2.2 you will see that the equation for spherical wave propagation, you can tell right there in the equation form. Profile of wave broadens gradually. Of course, is when you look at the spherical wave, you know, as it propagates outward direction, of course, the wave front is getting larger. And exponential decay of the shock wave. Before you getting into 2.2, I want you to think, before I really getting into there and explain, and this is when the R is really the it's called the standoff distance from the original charge location to the target point. The distance is called the standoff distance, S-T-A-N-D-O-F-F distance. Standoff distance exponentially decay. I'm talking this, I'm staying at the 1 point. Okay, that's a target point. And your explosion point is right here. This is the distance. Okay, I'm standing here. Then at the time of explosion, shock wave will just broaden up, propagate in radial direction, then hit it, then passing by. This is the profile, go up and down. This is where the shock wave hit the target. Okay? Then we are dealing with a millisecond. Everything will be done in 3 or 4 milliseconds, then done. But 500 feet away, one phenomena is called the surface cutoff phenomena. I'm going to put that in the, we have to give you some sort of midterm exam. When I say midterm, just a shock only, this underwater explosion only, and no gas explosion, no fire, because you wrote a really small project, you are writing small, investigating for your own project for the gas explosion. So only the exam I'm going to give you, maybe around, I haven't decided, before the final class, or maybe after final class, some exam I'm going to give you to cover, to check out whether you really understood or not. I'm going to really raise you a question about the surface cutoff, most important phenomena. If you cannot explain the surface cutoff, then you lost one important act, which is just here's appetizer. So then as it propagates, shock wave propagate, it's going to come down exponentially, and suddenly the shock wave cuts. It's not gradually come down to zero, some situation. It's simply cut due to the tension wave, or called the rarefaction wave, which is called the surface effect or surface cutoff. That I'm going to tell you in the section 3.2, somewhere there. And then it go down to slightly below 0, 304 psi, slightly below, then comes back up. So this is really small compared to the initial shock wave, and this is called the, could it be due to the bottom reflection or bubble pulse? What does it mean, bubble pulse? When gas bubble, as we talked Friday last week, not the week before, as the gas bubble grow, then shrink, then lose the stability and collapses. When the gas bubble collapses, what happens? It generates a small pulse. That's what the small pulse will generate. Slightly higher peak, but much less than the original pressure peak, but this is widened up a little bit. So when you talk about the impulse, okay, which is area under this pressure curve, maybe this may not be negligible, because the impulse is measure of the damage. So I said here, due to the surface reflection wave, or called the rarefaction wave, or tension wave, it's all same. So think about it ahead of a time where I'm going to explain in detail. Okay, surface cutoff. Oh, this is due to the surface reflection wave. Think about how when the shock wave hit the surface, how the wave gonna behave. So think a little bit. It's different from a gas explosion. I don't really see this kind of the phenomena in gas explosion, in a sense. And rarefaction wave and tension wave. Can you pull the water? Can you pull the water? How can you pull the water? Hunter, how can you pull the water?
Using the straw.
Straw?
Yes.
How?
I don't know your lecture.
I didn't personally try to pull the water, but I imagine what you can possibly do in the cup of water. you put not the paper, a little bit thicker than paper, and if you try to, well, you can put try to pull maybe, then maybe small vapor bubble you may be able to seize, pull. If you try to pull, is water is capable to resist on the tension? Yes or no? $5 chance to win. Can you pull the water? Well, a little bit. Water is not capable to be pulled, but it has a very small resistance. It's again for 3 or 4 psi, it can break off, but not that greatly meaningful. So rarefaction wave is the wave, the pulling the water. In this phenomena, I'll do a little bit on this. A little bit shower. Then, hey, Kyung-suk, you have a haircut. Much nicer look. Strange Yongshin. And explosion occurs right here. And my target point here, my small sub is right there, only a few people inboard. Then what happened? At the time of explosion, the wave going straight toward the target, that wave will arrive to the target first, right? Yes or no? Yeah. Bottom could be right here, bottom. Then at some point, the first wave which will reflect from the water, the way you learned in high school physics is, then you have to take the distance d, same d. This is like a mirror image. Then you can draw the line here. And I can say that and draw the line here. This is straight right here. Then the first reflection wave right on the free surface is this guy will hit. Then will come back down. So reflection wave is concerned, this is the first wave, reflecting wave to hit the target. Afterward, there are lots of other reflection wave will come in and hit. So as you look at this, this point is called image charge, right? I'm going to just give you just the idea, then you can work out a little bit. Okay, this shock wave along the line here, direct line, is called the incident shock wave. Incident wave, shock wave, of course. And it's compressing the water and hit it, okay? And this is a compressive, I'm going to put the positive, pressing down. And another wave which will reflect, this is compressing the water, this is a plus. A problem is right here, when it reflected, there is nothing to hold on the surface, okay? When the shock wave hit it here, one shock wave will come down here, hit the particle here, that particle will try to shoot in that direction. When you look at that point, when you consider particle right here, so when the shock wave comes all direction, the one wave which comes to, this is the wave, shock, the reflection wave hit the target first. So one guy tried to push the particle in that direction, but right here it will reflect. As it reflected here, so you assume this guy is image charges right there. Listen carefully. You learned in physics in high school, but may not really think about the cause. So right here, this particle is not only trying to move in that direction, but think this as an image charge, and this guy is at the same time trying to move in that direction at the same time. So trying to move in that direction. And the velocity, so as you look at this triangle here, that triangle, same standoff distance from the charge and image charge. So this velocity you anticipate V2 or U2 is the same. So if you just have a vector sum, then fluid particle right here is trying to move in what direction? Vertical direction, right? Right? Say yes, vertical. Then, so as I look at the motion along this line here, and along this line, look at the fluid particle here. Fluid particle, this is like attract, I call usually TTRAC, attracting source. This is attracting source. This source or explosive is compressing it. Think of this as attracting, okay? Has to dress really well. Has to be nice looking, Then will attract, this particle is attract here. As you look at here, this particle will try to move in the direction of image charge, and all the particle will try in that direction. This is water, and try to move towards that direction. So this along here, fluid particle is moving in the direction of the image charge. However, this shock wave front is moving opposite to the direction of image charge. You see that? So, but this kind of the incident shock wave, if you look at the fluid particle, this fluid particle is the same as the direction of the shock wave velocity. It's the same direction, but this portion, acoustic, the direction of acoustic wave or shock wave, which is moving in that direction, is opposite to fluid particle, the fluid particle direction of motion. Fluid particle is trying to move in that direction, but shock wave is moving to opposite direction, which is called the rarefaction wave. Rarefaction wave. And this is what, if it happen, effect is you try to pull the water. So which means the shock wave is from zero, then down in the opposite direction, and it comes back out. I'm not going to bother to write much here because it's coming back for detail in the earlier section of chapter 3. So that's what was happening. That's what this tension wave, negative pressure. Then suddenly you have positive pressure. Then when you have rarefaction wave then cuts off. Okay? Then it's a little bit below 0. Depend on this. If this is a dynamic pressure only, then it could go below 0 a little bit. It's few psi. So this is a typical pressure profile as you look at the test result. So maybe as a good measure, the Yonghyun may look at our explosion test. Then if you look at, you will see that surface cutoff phenomena. So if you can access on that test data, you can just print out and check out the surface cutoff and bring back, and we can share together. It's coming back, but a little bit appetizer. And the scaling law. This scaling law, again, chapter 4, we're gonna look at so-called the Hopkinson's scaling law. I mentioned this before when I talk about the gas explosion. Hopkinson's law, or which is really applicable very well to underwater explosion problem, to scale, to conduct a scale test or model test. This wording is a little bit, you have to think a little bit more to really get more feel. It said if this is the scaling law, or some people call the principle of similarity, same thing. If the linear size of the charge is changed by a factor of k, the pressure condition will be unchanged if the new distance and the time scale k times as large or as small as original one are used. Difficult to understand what that sentence really means, but I'm going to really explain details. The linear size of the charge, we have to understand what does it mean, the linear size of the charge. So in this example, I said reduce the charge size by a factor of 8. Reduce the charge size by a factor of 8. Or reduce the size of the charge by a factor of 27, for example. Let's look at, to understand the linear size of the charge, what that means is mg is what? Weight, right? Mg is the weight of the charge. Weight is mass times g is weight. Mass is rho times v is volume. And the g is invariant. G doesn't change, but if you say global sense, the g value here in New York would be different from the g value in Daejeon. But it's really a fraction of 1 g. If you look at maybe small variation, no differences. So you can say, well, assume same, invariant. Rho is mass density, invariant, no change, right? Makes sense. You disagree? I'm not talking about that rho value in the moon away from the space. No, we are talking in the vicinity. So rho invariant, G invariant, I can say mass is proportional to V. V is the volume, right? So the volume-wise is proportional to the length cube, right? Volume. L1, L2, L3, all product. So volume is L proportional to L cube. So here, L is length, linear size, length of the charge is changed by a factor of K. Really, we are talking about the factor of K, the linear size, which is the length, and replacing L by K, okay? So let's say volume, change of the volume with 8. 8 is L cubed, L is 2, which means K is 2. Volume is changed by a factor of how much? 8, right? But length is changed by a factor of 2, which is K. So if the volume is changed by a factor of 2 and it's 7, that's a volume. That's a 3 cube is 27. So linear size is concerned, the K is 3. Do you follow me? Nothing much in there. So in this case, reduce the charge by a factor of 8, then the K is 2. Right, 2 cube. So if you change the distance by a factor of 2, the time by a factor of 2, divide T by 2, okay, then the pressure condition, if this is original 300 pound charge, 2200, I still have 2200. Okay, when you reduce the bomb by a factor of 8, 37.5 pound TNT, you can use it to maintain the same shock pressure. Same shock pressure, however, you have to reduce the distance by a factor of 2. 2 comes as a K value is 2, linear size, and time you have to reduce by the K factor, which happen to be 2. However, tail end is different. Pressure magnitude is the same, but tail decay rate of the tail is different from decay rate from the reduced size of charge. Makes sense. But at least the peak pressure is the same. This is kind of the introducing the scaling law a little bit, but when you're getting into chapter 4, the Hopkinson's scaling law, then you can tell more form approach to really show the reality and the computational approach. Any questions here? Nothing much. This is increased charge by a factor of 8. This is increasing 50 feet. If I moved it to 100 feet, what happened? To get the same shock pressure, 300, you have to multiply 8. This case is reducing because it's getting shrink. This is increase, same thing. So read well. And this portion, motion of the gas sphere, Friday, before I took off, this is what I explained about the oscillation of gas bubble. And this sort of the equation is empirical equation. It's not really, this is really not computational is coming from the empirical, using the actual experiment. This T is period of oscillation of the gas bubble. K is a proportional factor, so T, period of gas bubble oscillation, is proportional to the E is internal energy of a gas to the 1/3 power divided by P is hydrostatic pressure to the 5/5. Okay, so this is just showing some relation how the period would be related with other physical quantity, internal energy, and P is hydrostatic pressure. But what the U.S. Navy did was develop the empirical equation set, which shows in the chapter 3, the section 1. Okay, I'll finish this page 12, then we'll quit. And this is a gas bubble size, and horizontal x is a time, and at the beginning, small original explosive size. As it explode, it will get really grow, right? Gas bubble grow, maximum, then down to minimum. Minimum size is slightly higher than the original size. Why? Energy lose, right? Energy lose in the water. So it reduced down to smaller, which is larger. Then energy is still trapped in the water. Then it expands again down to min. Right here, the gas bubble collapses. So this size is larger than this side because energies keep losing in the water. So it's moving like that. And this is still 300 pound the TNT. So this is a time axis, this is a depth, this is a free surface, and 50 feet below the water, an explosion occurs. As time goes by, you can see the slice. Slice is the size of the gas bubble. Okay, so if you look at cut this from here to here, that's the diameter of the gas bubble. It will grow, reduce down to min, keep going up, migrate to the free surface, and this is the center of the gas bubble. Okay, so motion is clear. This is measured. It's you can compute. It's not the problem. Okay, so I'll stop right here at page 12. I got a few things to talk to the Wednesday. I'll move on to 2.2, hydrodynamic relations. I'm going to go a little bit faster because you have learned the conservation law. Yes or no? Yes, but maybe all the content is evaporated, maybe. Then I'll, you know, that's what human nature. If you don't forget, you got something wrong. I'll bring back in your memory. That's what I'm going to do. And its important implications are there, which people doesn't know. Usually you start from wave equation. Okay, then you don't understand what's going on in the shock wave case. I'm going to show that this Wednesday.